Recording. So hello, everyone. So nice to see some of you and the rest of you. So nice for you to be here. We are continuing. This is now, of course, week number 8, which makes this lecture number, I believe, 14, because we missed one. We are on chapter 18, which is on inference in practice. And remember, at this point, recall from chapter 15, I believe it was 15. Let me go back and check. No, recall from 16. Recall from chapter 16 that we had one situation in chapter 16 about wanting, let me be more specific here. So recall from chapter 16, a population has an unknown mean mu. We wish to estimate mu. So we take a sample and calculate X bar, our sample mean, and then we form a confidence interval about X bar. We have X bar minus Z star sigma over the square root of n to X bar plus Z star sigma over the square root of n. And we have a certain level of confidence that mu is somewhere in the confidence interval. This is the idea of confidence intervals. We don't know mu, so we form a sample. We estimate it by finding X bar. And then what do we do with X bar? We form an interval around it and say, I am pretty confident that mu is somewhere between these two numbers. Now, what we didn't do last time, which we're going to do now, are the conditions that must be satisfied. To be allowed to do this, to form this confidence interval. And when I say that, obviously you can form a confidence interval anytime you want. But the question is, will the confidence interval realistically give you an estimate for what we're looking for or not? So what are the conditions that must be satisfied? 1, the sample must be from an SRS. What does SRS stand for again?
Simple random sample.
Simple random sample. We don't do volunteer response samples. We don't do surveys. We don't do convenience samples. We don't do stratified samples. Just keep it simple. Literally, simple random samples. Okay, 2, no practical problems like non-response. No practical problems like non-response. Okay, and in this class, if you're given a problem, especially on a homework or a test, just assume that it's okay. Don't invent problems unless the question literally calls for it. So it's got to be from an SRS, and we don't want to have any issues with the SRS. Everything is nice. 2, the population is large compared to the sample. The population should be large compared to the sample. Don't take a sample of size 5 from a population of size 7. Okay, the population should be large. If I want a sample of Americans, how many Americans are there? What, like 300 million Americans or something like that? So take a sample of size 1,000. So 1,000 is small compared to 1,000,000. Okay. Next, the variable of interest, the variable in this case mu, comes from a normal distribution. Comes from a normal distribution. Sigma is known. And that's it. Sigma is known, but mu is not. Okay. So essentially, it's got to be normal. It's got to be an SRS. And the sample should be small compared to the population. Okay. As long as you have those, the last two or the last one, sigma is known, but mu is not. If we don't know sigma, we're going to use a completely different formula. This is the one specifically for this situation. If these are all satisfied, then you are good to go. Okay, and this formula that we have here, that is your confidence interval. Your calculator does not know if it came from an SRS. Your calculator does not know if the population was big compared to your sample, and if there's any practical problems. Your calculator knows none of that, which means your calculator will give you an answer. I have to leave. Oh, go ahead. Go ahead. I hope everything's okay. Okay. Your calculator knows none of that, which means you need to check on your own whether or not you're allowed to make your confidence interval, and if so, go ahead and do it. If not, don't do it. Again, in this class, assume everything's okay. Next. Okay. Section 18.2 now. Cautions about confidence intervals is the title. Cautions about confidence intervals. Okay, so we know again, so recall that if I make a number line and I have mu here, my confidence interval, sorry, it's not mu, I apologize, it's X bar. If I knew mu, I wouldn't need to do a sample, I'd have my answer. So the right side is X bar plus Z star sigma over the square root of n, and the left side is X bar minus Z star sigma over the square root of n. So the margin of error is equal to Z star sigma over the square root of n. It's this distance here, margin of error, or this distance here, the margin of error. The margin of error is how far we go from the center to the left to the right. Now, the margin of error essentially is your uncertainty, right? This is essentially your uncertainty. Well, I got this value from my X bar, but it can be plus or minus this amount. I can go this way or that way. Essentially, what the margin of error is measuring is your uncertainty, how much you don't know. Now, uncertainty can come from two places. So margin of error comes from two places. Number one, random sampling errors, and two, practical difficulties like non-response or undercoverage, like non-response. or under coverage. Under coverage. Okay. So let me, I'm sorry, I have to replace this margin of error here with uncertainty is a better word here. Sorry about that. Uncertainty comes from two places: random sampling errors and practical difficulties. Okay, the margin of error itself, only takes into account random sampling errors, which is why you don't want to do this procedure if there are practical difficulties. If there's practical difficulties, you're not going to get a confidence interval which adequately represents the scenario. Because if there's practical difficulties, the margin of error is not going to take that into account. It's going to say, oh, here's your uncertainty, which is why I said essentially it's your uncertainty, because it's not really your uncertainty. There's more to it than that. The margin of error is, well, this is your uncertainty from random sampling errors. But if I had extra uncertainty for whatever other reasons, I'd have to make my margin of error larger. And in fact, next chapter, or in a few chapters from now, when we say, what if you don't know sigma? Well, that's a practical difficulty, not knowing sigma. So we're going to say, okay, you don't know sigma? Okay, we can get around that. Use this instead. But when we use that instead, that is a little more uncertainty, which is why the margin of errors we're going to see gets a little bit bigger. As of now, the margin of error only comes from random sampling errors. As we progress and do more sophisticated types of problems, we're going to see that the margin of error is going to change and it's going to grow to take into account other problems that might arise. If we have non-response or under coverage, or there are other practical difficulties, we would have to make it larger. But we don't have the math for that yet. We don't know how to incorporate that, so we're not going to do it. That's essentially what it comes down to. Okay, makes sense so far? Yes, no, maybe so?
Yeah.
Okay, so now, section 3, 18.3. Cautions about significance tests. So the first two sections were on confidence intervals. Now we're going to have cautions about significance tests. So let's recall exactly from chapter 17 what exactly a significance test does. Because remember, conceptually, significance tests and confidence intervals are very, very different. A confidence interval, we have no idea what the value is. So we take a sample and we say, we're pretty sure it's between here and here. Hypothesis testing is the opposite. We're pretty sure we know what the value is, but we're going to test it to make sure. Or, no, that's what you believe, but I don't think so. Either way, we come in with a belief of what the value is. So with significance tests, we start with a belief of the value of some parameter. What do we call that belief? Anyone recall what we call the belief? We had a name for it.
The null hypothesis?
Null hypothesis. This belief that we have about whatever your parameter is, we call the null hypothesis. We decide to test the null hypothesis versus a competing hypothesis or a competing belief. What do we call that competing belief?
The alternative hypothesis?
The alternative hypothesis. Labeled as? Anyone recall what we label the alternative hypothesis as? H1 was one possibility. We actually had two. Anyone remember the other one? HA. Good. HA for H alternative, or H1 instead of H0. So we
Professor?
decided, yeah, go ahead.
After the null hypothesis, what does that say? Is that
H0.
no,
That's a symbol for null hypothesis.
no, I mean the next line where you put null hypothesis after, so is that
We-
versus?
We decide to test we decide to test H naught versus a competing belief.
Versus, okay, thank you.
Are you saying my handwriting's horrible?
Yes,
Okay, cool, just checking. That hurts, just so you know. My second grade teacher, Mrs. Morris, would be very upset to hear that she gave me best penmanship award in second grade. To this day, it's still my crowning achievement.
it's okay, mine's not good either.
Wait a second, hold on. I can write good. See, I'm gonna write, give me something to say to write. I'll show you how I can write neatly. Go ahead.
How about you rewrite versus? Erase
Wow.
that and rewrite
Wow,
it.
that's cold. That's cold. How's that?
Okay, now do that for the rest of the note.
The problem is it would take me forever to
I'm
write.
just joking.
I'm sorry. I just have so much to say and I want to get through so much and I write quickly, but you're right. I should. Also, am I spelling belief right? It's looking wrong.
I think that's right.
I know it's I before E except after C, but not everything is like that. I don't know. Belief?
I think it's because you wrote it so many times now it looks weird.
Maybe. No, that looks even weirder. So I think, yeah, you're right. I think it's good. I think. All right, I'll try to write neater, but I make no promises. So we start with a belief of the value of some parameter, the null hypothesis, H naught. We decide to test H naught versus a competing belief, the alternative hypothesis, H1 or HA. So we take a sample. So we take a sample. I'll make it exclamation point. So we take a sample. Yeah, that's definitely an exclamation point sentence. Based on the outcome of the sample, we decide which hypothesis we will support. If we get a result very unlikely when H naught is true, we will reject H naught. What do we call a result very unlikely when H naught is true? What's a name for a result very unlikely when H naught is true? We have a name for that. Anyone remember? We call it statistically I'll give you a hint. It starts with the letter S and rhymes with magnificence. Yes, good, significance. Okay, that was a tough one. Okay, if we get a result very unlikely when H naught is true, we will reject H naught. That is called statistically significance. Otherwise, we will not reject H naught. Notice that we don't accept anything. There is no accepting. Either we will reject the null hypothesis if the result is unlikely when the null hypothesis is true, or we will not reject the null hypothesis. We don't accept, either we reject or we do not reject. Make sense? With me so far? Yes?
Yes.
So, warnings, here are my warnings. Okay. Small populations with large samples, small populations with large samples. What am I trying to say here? Small populations with large samples. How do I word this? You know what? I'm gonna rephrase it. I apologize if you wrote it, especially if you wrote it in pen. My bad. I'll write it like this. Because large random samples, have small chance variation. Because large random samples have small chance variation. Very small population effects can be highly significant if the sample is large. So write that down. And I'm going to write a couple others with it. Because small random samples have a lot of chance variation. Even large population effects can fail to be significant if the sample is small. And finally, number 3, statistical significance. Someone's writing something. Oh, yes. Okay. Statistical significance does not tell us whether an effect is large enough to be practical or important. So first write those down. I'll explain them in a second. So what it means is as follows. We're looking for statistical significance. In other words, we want a result that is really, really, really unlikely if the null hypothesis is true. Now, the bigger your sample, the more that we reduce the variation. We already know this because we always divide the standard deviation by the square root of n. So large samples mean small standard deviations, small variation, which means if I have small variation, what that's going to do is it's going to make my confidence interval, or it's going to make my region where I'm going to reject the null hypothesis very small. Okay, which means that the population, a small population effect could knock us out of that region and have a very a large or significant overall effect. If the sample is big, if the sample is really big, then the population comes more to the forefront. If the sample is very small, then we expect lots of variation. It's expected to have lots of variation, which means the population, which is really what matters, might not show its significance. It might not exhibit its true properties in regard to the test because a small sample size gives us a too large of an area not to reject the null hypothesis. Again, to recap, big samples mean that you kind of hone in on the true value. If you're honing in on the true value, the smallest population effect will be evident. Whereas if you have a small sample and you have lots of variation, then there's too much wiggle room. There's too much room for error. We're not going to reject the null hypothesis if there's lots of possibilities that the null hypothesis is true. So the null hypothesis might not be true, but you're not going to notice because your sample is too small. And if your sample is really big, it's very possible that the null hypothesis is not true, but the slightest difference in population will make us reject the null hypothesis. So if you have a large sample but a small population, problem. If you have a very small sample with a large population, problem. What you're looking for is a small sample and a large population, but a large enough sample not to have these effects. So you want a significant portion of the population, but not too big, not too small. Again, in this class, just assume when you have a homework question or a test question, unless it's specifically asking on this concept, that everything is satisfied and your statistical significance hypothesis testing is fine. That's basically the overall effect. The last part tells us that even if you do have statistical significance, it might not be practical significance. In other words, I think that Coca-Cola bottles, they claim that it's 2 liters in every bottle. And I do a hypothesis test. I think they're lying to us. It's not 2 liters. They're lying to us. So I do a test and I reject the null hypothesis because I think, or the data supports that it's not 2 liters, but it's 2.01 liters. Coke might say 0.01 liters, fine. Statistically, you're correct. The null hypothesis is wrong. It's not 2, it's 2.01. But we don't care. The amount of time it would take us to recalibrate all the systems is just too much work, it's too much energy for such a small reward. It's not worth our time. So just because there is statistical significance does not make it a practical significance. You have to decide on a case-by-case basis whether or not it's really worth it to make any changes or to do anything, even if you decide to reject the null hypothesis. Make sense? Yes, no, maybe so? Okay, good. Okay, next. Section 18.4. Sample size for confidence intervals. Sample size for confidence intervals. So we know the margin of error is equal to Z star sigma over the square root of n, correct? What if I decide, or I come into the problem and I say, okay, I haven't taken my sample yet. I haven't done it, but I want to make sure the margin of error is no more than 0.01. I want to make sure that my margin of error is not too big. My goal is to find mu. That's the goal of the problem. If my confidence interval is huge, okay, yeah, I narrowed it down from here to here, but that's still a pretty big range. So what am I going to do? I come in and I say, you know what? I don't want a big range. I want a small range. Well, looking at these three numbers, what are the three ways to make the margin of error smaller? How can I make the margin of error smaller? What are the three things I can do just from this equation? What are the three things I can do to make the margin of error smaller? Three answers to this. What are the three things I can do to make the margin of error smaller?
Is it changing your confidence level, like lower?
It's lowering the confidence. If I lower my confidence, then I make the margin of error smaller. I can do that, but I don't want to, because the less confidence I have, yeah, I can make the margin of error smaller, but now I have less confidence that my answer is correct. So I can do it, but I don't want to. I don't want to.
Making your population smaller?
If I make the population smaller, then I make my denominator smaller, correct? Wait, you said population, you said? What do you say?
Yeah, the N?
N's a sample size, right?
Sorry, yeah.
Okay, if I make, because I can't change the population. It's like, okay, well, let's just kill people so the population is smaller. You can't do that. That's not practical. Okay, that gets into whole ethical problems, which we want to avoid. Okay, so if I make the sample size smaller, I'm making the denominator of my fraction smaller, correct? Which does what? If you make the denominator smaller, what happens to the overall fraction?
It becomes bigger.
It becomes bigger. My goal here is to make my margin of error smaller, not bigger,
So you would do the opposite?
which is what?
Enlarge it?
Enlarge the sample size. Enlarge the sample size. This, yeah, I can do that. I can make my sample size larger. What's the third way? What's the third way? Anyone? The third way is to make or lower sigma. But this is unfortunately impossible, because how do you change an underlying feature of the population? Mathematically, I can make Z star smaller, I can make sigma smaller, or I can make N bigger. But you can't magically change, you can't change an aspect of the population. So while you'd love to be able to do it mathematically, you can't do it practically. So what's the conclusion? How am I going to make my margin of error smaller? Focus on N, sample size. So let's solve for n. Let's go back to the formula. How do I get n by itself? How do I rearrange? How do I manipulate this equation to get n by itself?
Multiply n to both sides.
Okay, multiply the square root of n to both sides.
Yeah, and then divide the margin of error to the other side.
So square root of n equals z star sigma over the margin of error,
And then square both sides.
and then square both sides. So a few of you were saying it in chat, which is good. So n equals z star sigma over the margin of error squared. So let's do an example. So we had an earlier example. We had an earlier example where n was 20, sigma was 2. We had 90% confidence. And we concluded from this, without even caring about the details of the problem, that the margin of error is what? We can do this. We have a formula. We need n, which we have. We need sigma, which we have. And we need z star. Now, what is the z star for 90% confidence?
One 1.64.
1.645. That was the number we used, correct? Right? So 90% confidence implies z star equals 1.645. Remember, we had three numbers, 90%, 95%, 99%, that you guys should know, be able to recall off the top of your head. Yes, Cynthia, go ahead.
I just want to say something because on the homework I kept getting it like the questions wrong, but I realized it's because on the notes I had written down 1.64. So I just want to let everyone know that you need to put 1.645 or else they'll mark it wrong.
Did I not do 1.645?
No, that's not. No, I didn't write. No.
No, we just had 1.64.
So yeah, because
I guess I didn't round to enough digits, so my apologies on that one. It should be 1.645. So thank you for pointing that out. If I had forgotten to use enough digits for that one, certainly 1.645. So thank you. So 1.645 times sigma, which is 2, divided by the square root of 20, and then squared, gives us a margin of error of how much? What does the math give us? .54, approximately 0.54. Okay, so this says that whatever the situation was, the margin of error is 0.54. That's an earlier example in the book. And you come along and you say, oh, sorry, guys, sorry, but 0.54 is way too big. That doesn't narrow down what I'm looking for too much. Okay, I want something less than 0.54. I want a margin of error equal to, let's say, 0.3. That's all I'm willing to accept. 0.3, nothing more than 0.3. So the question is, what size sample should I use? If I don't want any more than 0.3, what size sample should I use? So what do I do?
You just plug it back into the equation, but you plug in the margin of error as 0.3.
Okay, So if I go back to this equation, I get n equals z star, which is 1.645, times sigma, which is still 2, divided by 0.3 squared. What does it give me on your calculator?
I got 120.267.
Okay, I got 120.27 approximately, right?
Yeah.
Okay, so you're gonna have to ask 120.87 people. Now, I'm not sure about you. I don't know where you're gonna find 0.27 people. Which means we gotta actually choose either 120 or 121 because you can't ask 0.27 of a person, right? So are we gonna pick 120 or 121? So Cynthia, you say 121. Round up both ways. Okay, so, okay, well, that's great. Why don't you round down? Isn't 120 closer than 121?
I thought you said like in this scenario. I don't know. Yeah, this scenario we always have to round up.
That's true, but could you tell me why we round up?
Not really. That's all I remember.
Okay, the reason is 120.27, that exact number is the cutoff between having a margin of error of 0.3 or having too big of a margin of error. The bigger the sample size, the smaller the margin of error gets. The smaller the sample size, the bigger the margin of error gets. When I say I want a margin of error of 0.3, do I really care if it's even smaller? If you give me a smaller margin of error, would I be happy? Or would I say, sorry, that's just too small. I really wanted 0.3. No, I don't mind going smaller. I mind going bigger. So if 120.27 is the exact number, but something smaller than 120.27 gives me a bigger margin of error, and something bigger than 120.27 gives me a smaller margin of error, I'm always going to go bigger because I always want the smaller margin of error. So that's why we always round up. The answer would be, sorry, not 20, but 121 people. That will give me the margin of error that I'm looking for. Does that make sense?
So on homework problems and stuff like that, it's gonna want us to round up.
Always. You're not rounding. See, that's the thing, is you're not rounding. If I'm rounding, then the answer would be 120. I'm not rounding. I'm deciding to go up because going up makes my margin of error smaller, which I'm okay with. Whereas going down makes my margin of error bigger, which I'm not okay with. So it's not rounding, it's a conscious choice about which direction you're going. Does that make sense? Everyone, does that make sense? Now, if you say round up always, I know what you mean. You'll always be correct in this scenario. When you're looking for a sample size, it's never a bad idea to round up. Because the more people you have as a general rule, the better your sample is going to be. The smaller your margin of error. Does that make sense? Okay. All right. Moving ahead. 18.5. The power of a statistical test of significance, what we're calling a hypothesis test, the power of a hypothesis test. The power. It really sounds a lot more fancy than it actually is. The power of a test against a specific alternative is the probability that the test will reject the null hypothesis at a chosen significance level alpha when the specified alternative is true. So first write that, and then I will try to explain it as best I can.
What does it say after the null hypothesis? The HO?
At a chosen significance level.
Thank you.
You're welcome. Sorry, Mrs. Morris. Okay, so at a chosen significance level, alpha, when the specified alternative is true. And here's what we mean by that. Suppose we have a null hypothesis where I'm going to try to do an example that they have in the book. Mu is equal to 0. So somebody comes into play in a certain situation, somebody comes along and says, null hypothesis for some situation, whatever it is 0. And you come along and you say, no. I really don't think that's true. I think that mu is greater than 0. Do you specify right now which value greater than 0 you're claiming it's going to be? Or are you just claiming it's greater than 0? Right? You're just claiming, I don't think it's 0. I think it's bigger than 0. Which is fine as statistical tests go. But when it comes to the power of a test, we are looking at a specific alternative. So I might ask, what is the power of the test, or just the power, when mu is actually equal to 0.8, which is certainly one of the numbers greater than 0. So the power of the test against a specific alternative, in this case, 0.8, is the probability that the test will reject H0 at a chosen significance level. So suppose alpha is equal to, in our case, 0.05. What does this mean? Alpha, the the significance level is 0.05. In the context of hypothesis tests, what does it mean to say alpha equals 0.05? What does this mean? This means if the p-value is less than 0.05, reject the null hypothesis. That is what the significance level is. It's telling you the cutoff. Remember what the p-value is, right? The p-value is that number that we get. And if we get the number too small or small enough, we reject the null hypothesis. How small is small enough? Remember what I said? If they don't tell you, assume it's 0.05. Well, if they do tell you that it's 0.05, that's fine too. But alpha, the significance level, is that choice where if it's smaller than that number, we reject the null hypothesis. And if it's not smaller than the number, then we don't reject the null hypothesis. So let's say we go ahead and take a sample. Suppose the sample size is equal to 10. And suppose that sigma Because right now we only know situations where we know sigma as well. Suppose sigma is equal to 1 for this particular example. So I want you to imagine a normal curve. If H naught is true, if H naught is true, if H naught is true, then what's the mean of this distribution going to be?
Zero.
0. Now, we want to reject the null hypothesis if we get a value that's what? Small, less than 0, like way to the left or way to the right of this distribution? What values will we say, well, based upon what I got, I'm going to reject H naught and claim the mean is really greater than 0? Would I want to get values on the left of this distribution or the right of this distribution?
The right.
The right. I would want to get positive values. If I get positive values, I'd be much more likely to claim the mean is really greater than 0, correct? If I got negative values, I'm on the wrong side. Agreed? You guys with me or no?
You took his history? Guy looks like hardcore. See him.
It's not that bad.
What book?
Not that hardcore, I promise.
Hilarious to watch him try and talk. I asked him anything I could think of. Favorite color? Blue. Favorite.
This conversation is better than mine.
Trust me, you never know what fact may prove to keep saving your life. Blue.
Mariah?
Blue. Yeah.
Oh, come on, that conversation was great. It's much more exciting than mine. Anyways, so if I get values on the right side of the graph, positive values for my sample mean, I'd be much more inclined to claim that the null hypothesis is false, right? So I'm looking for values on the far right of my distribution. Anywhere in the top 5%. Why 5%? Because that's my alpha. Agreed? Now, what's the cutoff z-score? I'm curious. What's the cutoff value for that top 5%? Okay,
Would it be 1.64?
1.645. Let's go one extra decimal, 1.645. So if I get an X bar, or if I get a z-score that's past 1.645, I'm in the far right 5% of the distribution. I would be very well justified in saying that the null hypothesis is incorrect. Agreed? Now, if the alternative hypothesis is incorrect, if mu is really 0.8, if mu was really 0.8, then where should the center of my distribution be? If mu was really 0.8 and not 0, where would the center of my distribution be?
Slightly to the right.
How far to the right specifically? You give me the exact value of the center.
Before 1.
Be more exact. Where's the exact value of the center? .8. If mu is really 0.8, then the exact value of the center should be 0.8, which is right over here. Agreed? Yes?
Yes.
Which means that in reality, it should look like that. Right? If it's really 0.8, it should shift to the right. Actually, you know what I can do? I can do this. I could copy it and duplicate it. First, let's get rid of those extra words there. And I don't want this, and I want that or that. Oh, no, don't do that. Okay. Oh, love this. So I can take this guy and move it so that it's centered at 0.8 instead. And let's make it a new color so that we can distinguish it. So if mu is really 0.8, then this should be my graph, not the original, right? Yes? Yes?
Yes.
Yes.
Okay, well, where would I reject the null hypothesis? I'm going to reject the null hypothesis if I pass 1.645. But on my new graph, that's a lot more area. On my new graph, passing 1.645 is a lot more area, correct? Again, the power of the test is the probability that I'm going to reject the null hypothesis at a certain significance if the specified alternative is true. Well, what is the area underneath my new graph? How would I calculate that? How would I calculate that?
Would you use the second and then the varies on the calculator, on the graphic calculator?
So let's go ahead and do it. Let's go ahead and do it. Of course, what sigma are we going to use here? I don't think I took it into account, unfortunately. I forgot to do it in the first case. Actually, 1.645 is still correct, but let's keep going. What area is that past 1.645? You can do it in two different ways. The book does it one way. I'm going to do it a slightly different way. What's the area past 1.645 if the mean is really 0.8? .199. We've gone from 5% to 20%. We've gone from 5% to 20%. So notice that what happens is that the area, the rejection region, we'll call it the rejection region, the area or the portion on my axis for which I will reject the null hypothesis, gives me a larger percentage if the alternative is really true, which it should, right? I mean, if it's really 0.8, shouldn't I have a higher likelihood to reject the null hypothesis? Yes, no, maybe so. You guys with me, or have I lost you?
I'm lost.
You're lost. Okay. Here's what we're gonna do, because it's 5:05 and I said I'd give you a half an hour for the quiz and I gotta go anyways. Let's just start back from here next time, 18.5. And we'll finish 18 and do some of 19 next time. But if you didn't get this, don't worry. We'll start from here next time. Okay, so the quiz is up. So you can get started immediately. I'm giving you the next half an hour to do this. Will this still, yeah, I'm still gonna post the whole lesson. But I'm not gonna do it till tonight because I have to leave now. but I'll still post the entire lesson, and we will just redo 18.5 next time and then move forward. No, the exam is this is not an exam. This is a mini quiz. You have 30 minutes to do it, although I think people who did it already, was there a time limit on it?
Yeah.
Yeah, it's a half an hour. So once you start it, you have a half an hour to do it. Okay, 30 minutes. That's the way it's set internally. I can't change that. Okay, so as soon as you start, you have 30 minutes to finish it. If you don't want to do it now, that's your choice, but you have till midnight tonight to finish it. Okay, I'm just giving you this time now so that I can be, have a clear conscience about making sure that you have time to do it, huh?
Thank you.
You are welcome. How many questions? I don't know. I mean, enough that I feel that you can do it in a half an hour. That's the best I can say. Have your calculator handy, Stephanie. Sorry, something in my throat there. I'm sorry. But make sure you have your calculator because it'll probably come in handy. Okay. Other than that, I will see you guys on Thursday.